Okay, this is redox, and the first topic is oxidation numbers. Okay, redox is a two-part series, and this is part one. So, redox stands for actually oxidation and reduction. So, oxidation, reduction, and we'll get to that in the second part. But right now, the first part in the building block of understanding redox reactions is to know about something called oxidation numbers. Okay? So, a redox reaction. In a redox reaction is any chemical reaction where one or more electrons transfer between two atoms. So a single replacement, a double replacement, a combustion, all of these can be redox reactions, as long as the electrons are transferring somewhere and moving around. If there's no electron transfer, then it's not a redox. Okay, so a big question is for us is how do we know when electrons are transferring in a reaction? You know, the reaction on your paper is not going to tell you that electrons are transferring. So we need to be able to find that out. And we find it out by using logic. So if the charges of elements change during a reaction, that means that electrons moved, right? Remember, when an atom becomes an ion, it's because he lost or gained electrons. So if charges change, if I move from +2 to nothing, that means electrons had to move somehow. So we are going to be finding charges of every single element in a reaction, and we call these charges oxidation numbers, or sometimes you'll hear it called oxidation states. So that means for redox reactions, we will have to calculate the oxidation numbers for all compounds in a reaction in order to find out what is going on. So let's take a look at how to calculate those oxidation numbers, how to calculate the charge for any compound. Okay, so here's a little diagram of what's going on in redox reaction. Okay, so I'll wait till it clears again. First, you have a sodium and a fluorine atom, neutral. Remember, the fluorine steals sodium's atom, and that makes both of them charged. And then that charge makes them attracted to each other. That's called an ionic bond, when you make two ions and then they bond. So you can tell that electrons are transferring, are moving around. That makes it a valid redox reaction. Okay? And so then oxidation numbers are charges. So you'll see right here, after it transfers, the oxidation on sodium is +1 and fluorine is -1. Okay, so that's what we're trying to find out, is oxidation numbers. So here are your rules for assigning oxidation numbers. The first rule is that any element by itself is 0. The oxidation number is always 0 if it's an element by itself. It's like hydrogen gas is H2 or iron, Fe. They are not bonded, they are by themselves. A pure element is always 0. The next rule. Most of the time, oxidation numbers are just the normal charge of the ion. Like in sodium chloride, NaCl, sodium is +1 and chlorine is -1. Those are the oxidation numbers, and that's exactly what we would expect the charges to be, so they're the same. And again, though, that is most of the time. And now we're going to talk about some of those exceptions. So here's some weird ones. Oxygen is 99% of the time, almost always, will be -2, except in peroxides. So like H2O2 is hydrogen peroxide. And then in hydrogen peroxide, oxygen actually has a charge of -1. So again, it's a little weird. So unless it says peroxide, though, you can assume that oxygen will always be -2. Another weird one like that is hydrogen. Hydrogen is almost always +1, right? You'd expect it to be +1, except if it's a metal hydride, like sodium hydride, because now it's acting as a nonmetal anion, and so its charge is actually -1. But again, if you see hydrogen and it doesn't say hydride, then you can assume that it will be positive 1. Okay, super important. This is the whole basis of what we will do with this. The sum of the oxidation numbers in a compound should always be 0. Okay, that means NaCl, remember sodium is +1, chlorine is -1, and guess what? The sum is 0. There you go. So that's going to be how we find it out. It's very similar to when we were figuring out Roman numerals for nomenclature. Remember, all the positives, total positive has to equal total negative. So when you add them up, they always equal 0. Okay? The exception is that if you are talking about a polyatomic ion, the sum should always be the charge of that polyatomic ion. Okay? So cyanide, which is Cn-1, that's a polyatomic ion. The sum should always be equal to this, -1, because that's what the whole thing is. It's not 0. See, there's nothing up here. This is 0. This is actually -1. So carbon is, remember, plus or -4. So today it's +4. And nitrogen is -3. And that should give you -1. Okay? So let's move on to some examples. Okay. So example number 1 says, assign oxidation numbers to all of the atoms in the following compounds. Remember, oxidation numbers means the charge that they're acting as. So look at calcium chloride, CaCl2. So the first step would be to say, well, we know the sum has to be 0. Okay? The second step would be to plug in what we think the charges are going to be. Well, calcium is normally +2. Chlorine is normally -1. I have 2 of them though, so I'm going to multiply -1 times 2. 2 plus -2 is 0. Is it 0? Yes. So that means we were right. Calcium's oxidation number will be +2, and chlorine's will be -1. So now let's look at this. If you remember names, starts with an H, always an acid. NO3 is nitrate. Remember what I ate made me sick, so it becomes nitric acid. So let's do the same thing that we did. First, we're going to recognize that the total needs to equal 0. The sum must be 0. Now let's plug in what we normally think that each of those elements will make. Okay, hydrogen makes a 1. Nitrogen is -3. Oxygen is -2, but there's 3 of them. Okay, so now when you add this up, do you get 0? 1 minus 3 is -2. Minus 6 is -8. So it is not equal to 0. So what are we going to do? Well, remember that hydrogen and oxygen are always equal to +1 and -2 unless it's a peroxide or a hydride, which this is not. So we can assume hydrogen is +1, oxygen is -2. So that means the one that we don't know about is nitrogen. So I'm going to replace nitrogen with a question mark. So +1, I don't know, and then 3 times -2 is -6, equals 0. Okay, so when we solve for that, like in algebra, solving for x, we get that it's actually 5. So that means nitrogen, even though normally is a -3, today it's acting like a +5. So our answers for the oxidation numbers, hydrogen is +1, nitrogen is +5, and oxygen is -2. Okay, so here's 2 more examples. This time, we're kind of throwing in some polyatomic ions to be tricky. Okay, so SO4 -2, which is called sulfate. So it's a polyatomic ion. That means the total needs to actually be equal to -2. Okay, so let's again plug in what we think. Sulfur is -2 normally. Oxygen is also -2. Is -2 plus -8 -2? No way, Jose. So again, oxygen we're going to assume is -2, but sulfur, I don't think so. So we will replace sulfur with question marks plus 4 times -2 is -8 equals -2. So what does this have to be to make that true? Well, it needs to be +6. So that means today our oxidation numbers in sulfate are sulfur is +6 and oxygen is -2. Okay, now let's look at a very complicated one, probably the most complicated one you will see. And it is ammonium carbonate, right? NH4 is ammonium, CO3 is carbonate. So I'm actually gonna do a little shortcut. Instead of doing this whole thing equal to 0, right, because compounds should equal 0, I'm gonna actually break this up into its two polyatomic ions, which is ammonium and carbonate, right? NH4 1 plus and CO3 2 minus. So I'm going to tackle each of them separately and then just put all my answers together. So you guys, I trust in you. We're going to follow both of them at the same time. Okay? So ammonium is NH4 plus 1. So we know that the total needs to equal 1. CO3, the total needs to equal -2 because those are the charges. Okay, I'm going to plug in what I normally think. Nitrogen is normally -3. Hydrogen is normally 1. Carbon's normally -4. Oxygen's normally -2. 3 oxygens, 4 hydrogens. When I add them up, do these equal each of those? Well, the first one, yes, it does. The second one, no. So let me continue on with carbonate then. Again, I'm going to trust that oxygen is -2 because it's not a peroxide, it's a carbonate. So 3 times -2 is -6. And so what do I have to add to it to make it -2? Well, +4. So that means, remember, carbon can be plus or minus 4, so today it's going to be +4. So now that I know that my oxidation numbers are going to be nitrogen is -3, hydrogen is +1, carbon is -4, or +4, sorry, and oxygen is -2. So here is what we're going to start getting into. Example number 2 says, assign oxidation numbers to each of the atoms in the following reaction. So what we're concerned about is reactions, right? So we're going to be given a reaction like this, and they're going to ask us, hey, what are the oxidation numbers for each of these reactants and products? So take a second, pause the video, work your magic, try it out for yourself, and then press play. Okay, so I hope you actually did it, but let's work this out. Iron is a standalone element, so it will be 0. Oxygen, also a standalone element, it will be 0. Iron oxide, okay? Remember how we had to calculate the Roman numerals and we said the total negative had to equal the total positive? It's the same process, okay? Oxygen is -2, so that means I have -6 over here. And so that means iron's going to be +3. So just like we did last unit, we're doing this again. And so here are your oxidation numbers. So here's another follow-up question. Did a redox reaction occur? Remember, redox means that electrons moved around. And the answer is, you bet. Okay, remember the oxidation numbers changed. Iron changed from 0 to +3, which means electrons had to move somewhere. And oxygen changed from 0 to -2, which means we had to be flip-flopping electrons around. Somewhere they had to move around, so yes, a redox reaction did occur. Okay, that's the end of this first video. There's a second video getting more into reactions and actually naming oxidation and reduction agents and all that fun stuff. So look forward to that and have a good evening.